Hi all. In this video, we see a paper titled Driving Behavior Planning and Trajectory Generation Method for Autonomous Electric Bus. So, in this paper, they say that they claim they develop a novel framework for path planning, which includes building up a high precision map in ArcGIS setup. Then they compute a global optimal path using a global planning. Then for local planning, they used double layer finite state machines for modeling driving behavior in behavior planning. And they utilized a parameterized cubic polynomial for the local trajectory generation for the path tracking. So autonomous driving has given safety and convenience for human beings. There is no doubt in that. And compared to self-driving cars, which is a little bit complex, building an autonomous bus seems to be relatively simple for the reason that it has a fixed route and the speed is low compared to the cars, and they also have some short distance within an urban areas. So here, in future, what would happen is a driver can become a safety officer, and his task would be to make sure the bus runs autonomously properly, so that we can be away from the manpower fatigue. So normally, for building an autonomous vehicle, there can be a two planning. One is global path planning and the local planning. The global path planning builds routes using a high precision digital map. There are many global path planning algorithms out there in the current setup. Among them are artificial potential field, cell decomposition, visibility graph, Voronoi diagram, and probabilistic roadmap. So these things, what the common among this is they build nodes with connected edges and weighted graph, and from that they try to build an optimal path. There are other path planning algorithms which are a bit faster compared to the earlier descriptions, like probabilistic roadmap method or RRT, random exploration random tree. But these things, although they are computationally effective, they are suboptimal or even a bit very far away from the optimal and jerky and not continuous path. There are also attempts have been made to utilize some kind of a genetic algorithm like particle swap optimizations, and also some kind of a memetic multi-objective optimization algorithm, so build the global optimal solutions. But the only concern bottleneck would be related to the high computational cost. So coming to the local planning, as we mentioned earlier, there are two parts. One is driving behavior planning and tree generation. In terms of driving planning, there have been many attempts have been made to mimic human-like decision making, like how to handle the intersections, roundabouts, and they have been attempts to make this kind of decision making utilizing a decision tree. But the most popular would be to build up a finite state machines, which has a sequence of driving behavior, and it goes to the particular state based on the situations and and driving scenarios. Coming to the second part of the local planning, trajectory planning, there are many attempts have been made to generate using curves, the mostly polynomial Bessel curve, splint curve, and here we use a parametric trajectories with some certain constraints, and if we are going into a purely optimization, there would have to go for a greater complexity. But in this paper, we try to build up a road network using ArcGIS framework to compute the global optimal path. Later, for local planning, we have used a double layer finite state metal machines for mimicking a human-like driving behavior. Later, for trajectory generation, they want to go for a faster reaction time, so they build up a simple cubic polynomial parameterized curve, and the parameters are identified using geometrical constraints. So the framework is depicted in figure 1. Like they build a map using the GPS IMU data, and the global path planning is computed using standardized algorithm. Once that points are being computed, then local behavior planning drives in what state it has to go based on the perception informations, and the local optimal trajectory utilize this global information to make a local trajectory planning, and that has been given into the path tracking controller. So this is what it's been informed information given in these descriptions, and they build map using ArcGIS framework, and the path is divided uh, into edges and nodes, and the nodes are connected through unweighted edges, and and it has a two path. One is general path, which has some kind of a straight line segments, and among the many GPS data points, as a uniform interval of data points is collected and being built up as a roadmap. And a special path is something like during the intersections of the curvature path, where this special path is being stored in a special database called a special path database, which has entry and exit point. Through this entry and exit point, we can see how what kind of can identify the intersections, and the corresponding driving behavior can be invoked using a double layer finite states machines. So these are the things. These world coordinates can be converted to local coordinates for the local trajectory generations. That's what they have given mention in these descriptions. And this is the transformations from the global coordinates to the local coordinates. And even for the opponent vehicles, they will be converting into this, and we will see whether the opponent vehicles are in within that zone, and within the zone, that corresponding finite state layer will be invoked uh, to the corresponding driving behavior. So this is a double layer straightening. The top layer is a simplistic one, whether we are in a general path or in a special path. So on the bottom layer will have some different states, and the different states will be like going straight, lane following, overtaking, merging back into the lane, and how to handle the intersections. All those things are being embedded in here, and these are the different things to transform into the different states, whether the vehicle is moving in front of the obstacles, that there is kind of a buffered road or a static obstacle, or overtake has to be done. So these are the different uh, uh, transformation that will be invoked based on the scenarios, and based on this transformation, and the state of the vehicle will be going into any of these six states. And once this done, then the mission will be completed. Again, then another starting will be given. The starting always will be in like kind of a structured and lane keeping. So this is something like kind of a collision checking. It will make some kind of box, and it will identify what are the objects within that box subjected to risky factor for the collisions. So related to operating, they fix with a simplest setting. They try to make a cubic polynomial fitting for the collecting based on the state of the vehicle, but on the current locations, and the path is given from the global path. So then a target point is fixed using the target point information like x, y, and theta values, this coefficient, and also how much offset from that reference path, and corresponding coefficients of these four coefficients are being identified using the geometrical information from these things. Once those informations are identified, a and a1 are becoming 0, and a2 and a3 are identified using the information from the target point and the offset of the vehicle from the reference path. So these are the something like the how it depends upon how the heading of the target point and the heading of the vehicle. So these are something for the fixed point. So this is the algorithm for that optimal trajectory generation. So once these three parts like global path planning and driving behavior planning, and also the local trajectory generation has been uh, setup, the algorithm setup, they try to test it in some kind of a simulation setup, and they felt it seems to be a promising one, and it can able to compute within a stipulated time, because they are using a simplistic one. and this graph shows that trajectory planning is really a cubic is sufficient enough to do the tracking even if the vehicle is offset from the uh, global principal trajectory. So path tracking, they haven't informed what type of path tracking to for the longitudinal and the lateral accelerations, but it can be a straight thing that for behavior planning can give you what velocity has to be adapted, and for path tracking we can have a standardized path tracking like a pure pursuit for this cubic polynomial trajectory. So field test also they did in some kind of a fixed setting in a city, something like so, and they felt like that the speed of the bus can could able to constantly adjusted based on the information from the vehicles and using those driving behavior and the curvature of the trajectories. And they also mentioned here that controllers, what kind of controllers has been have not been described here, but possibly they will be using a geometrical based or maybe an optimization based like an MPC. So this some of the pictures that how overtake lane change happening, how the overtake is happening in this vehicle is being slow, and how it is merging back into the principal lane. So the conclusion would be is they have described this proper path planning in a very elegant way, and the framework has three parts. One is the global planning, and they use ArcGIS platform to compare the global path, and the local planning have two parts. One is driving behavior. They use double state machines, finite state machines, and the trajectory generation is based on the cubic polynomial with certain constraints from the geometrical side. And future, I think they are planning to improvise the enforcement learning to build up a more driving logic for the driving behavior to handle some kind of an emergency scenarios. Thank you.